velocities expressed in the Earth axis. This is the equation that we used for question 4 of this tutorial. However, this question asks us to determine the value of this vector, of the vector v. So the velocity is calculated from the Earth frame of reference. So we need to convert the transformation matrix so that we have a system which is like this. Now we know that the relationship that exists between these two matrices is what? What is the relationship that exists between these two matrices? How do we find one from the other or vice versa? Is this equation here correct? No. So what's missing? Transpose or inverse? Yes. So the relationship that exists between the two transformation matrices is that one is the inverse, or in this particular case, the transpose of the other. We can say that the inverse is the transpose because the matrix is orthogonal. So if we take the transformation matrix, we will find equations for UE. Actually, let me write the entire matrix. Okay, so this is the relationship between the velocities expressed in Earth inertial frame and body frame of reference, UVW, and this is the transformation matrix that allows us to go from one to the other. Now, the question gives us some data. It gives us the pitch, yaw pitch, and roll angles, which are 0060. Angle of attack alpha, which is 30 degrees, and the side slip as 0, and the airspeed as 120 knots. Okay, so with this we have psi equals 0 and theta equals 0, so this transformation matrix, we can simplify it so that we have, this is cosine 0, cosine 0, so this will become 1. This is cosine 0, sine 0, this becomes 0, and this becomes 0. Here we have sine of theta, which is 0, so this first term is 0, and then sine of psi, which is 0, so all this 0. Sine theta, sine psi 0, and this term will be 1 times cos phi, what we leave as cos phi. This one, sine phi, cos theta, so this will be sine phi. And here we have 0, 0. This will be 0 minus sine phi. And this will be 1 cos phi. Okay. So the transformation matrix becomes somewhat simplified. 1, 0, 0, 0 cosine phi, sine phi, 0 minus sine phi, cosine phi. Okay, everybody with me? Yes or no? Yes. Okay, good. So now let's see what is the relationship that exists between the inertial velocities and the body velocities with these conditions. So for UE, we have that it is equal to U. For V, we have that V is equal to V cosine phi minus W sine phi. Okay. Do I need to do, yes, I need to do WE, which is minus, V sine phi plus W cos phi. Okay, so what we are interested in for the question is this last term, the vertical velocity. So we need to find W. So how can we do that? What equations do we know give us the values of the components of the velocities? There are three equations that we can use that are linked to these three parameters. One is the velocity equation, which is this one. Then we have the angle of attack, which is equal to what? W divided by U. And then we have the side slip angle, which is defined as V over dF. So this is equal to 30. This is equal to 0. Okay. So if the side slip angle beta is equal to 0, the velocity component along y will be 0. So this term and this term disappear from the equations. Okay. So I need to find W, which I can find from this equation here, but before that I need to find U. So I have these two equations. One, dF is equal to U squared plus V squared plus W squared. We can take this away because we know it's 0. And then we have the tan alpha is equal to W over U. Okay, so we have a system of two unknowns, U and W, two equations. So I solve one, substitute into the other, and we find that okay, sorry, oh yes, U is equal to 130.9 knots, and W is equal to 60 knots. Okay, so with this value of W, we can go into this equation to find the WE, the vertical velocity in the z direction, is equal to W multiplied by the cosine of 60. It was 60, yes, which is 1/2. So WE is equal to 30 knots. From these two equations. Okay, so you have this equation that is U squared plus W squared is equal to 120 squared. Yes, so you solve,
Oh, okay.
I don't know, you go U tan alpha is equal to W.
Okay.
So you put this in here, and you find out that U is equal to 131. You go back to this one and find the value for W. Okay. Any other questions? No? Yes. Yes, so tan 30 times U. That's a number. Okay. So this equation here becomes U squared plus U squared tan 30 squared Okay. Any other questions?
Only W.
No? Okay, did anyone do this? Right. Yes?
Yes.
Okay, good. Next one. We are given a set of equations, and the only information that we have is that the angle of attack is equal to 5 degrees. And then we have the measurements of the steady state conditions. So, AX, AY, AZ are equal to 0, 5, minus 3. P, Q, R are the angular velocities. They're equal to minus 1, 2, 3.5. This is meter second squared. This is degrees per second. And then we have the location of the accelerometer pack, which is 5, 0, 1. Okay, so this is the data for the question. We have to do is to reconstruct, so determine the airspeed, the F, and the side slip angle, beta. So we need to find these two equations, these two parameters, using the kinematic equation given in the question. So what we need to do here is to simply take the values that are given in the question and substitute them into the equations, the kinematic equations that you have been given. So, u dot 0 is equal, I'm doing this for x. Okay, this is the first equation. So, u dot is 0, which is equal to ax 0 minus, then we have q times w. So q is equal to this value here, 2. Now, be careful, because this is expressed in degrees per second. So, what do we need to do? We need to change it into radians per second. Okay? So we need to divide by 180 and multiply by pi w plus RE plus R is 3.5 degrees per second. So we have 3.5 over 180 divided by pi times pi b. Then we have plus the x distance for the accelerometer pack, which is 5 meters, multiplied by q square plus r square. So q square is 2. And r square is 3.5. Then we have minus y, which is 0 here, multiplied by the two angular velocities. And then we have minus z, which is 1, multiplied by p and r. So p is equal to minus 1. And r is equal to 3.5. Okay, so this is the first equation. I've simply substituted the numbers given in the question into the kinematic equation for x. Okay? Everything clear? Yes? Because you're in steady state, so there is no acceleration. There is no acceleration as measured on the aircraft. Okay, because here you have absolute acceleration as measured from the ground. But the terms u dot, v dot, z dot are the accelerations measured on board the aircraft, and they are 0. Okay. Shh. Sorry? No. If your velocities u, v, w are constant, then u dot, v dot, w dot are 0. Okay. The question mentioned that the aircraft is in steady state. It means it isn't accelerating. Okay. In general, you can always consider u dot, v dot, w dot, and omega dot, so the angular acceleration, as being 0, unless clearly specified in the question. Okay? So this is the first equation. Now I do for y. V dot, 0. Then we have ay, which is 5. Then we have minus r times u. So minus 3.5 over 180 pi u plus pw plus p is minus 1. And then we have w. Then we have minus x multiplied by pq. So this is multiplied by minus 180 pi, which is p, and q is 2 over 180 times pi. Then we have y, which multiplies p squared and r squared, but that is 0. And then we have minus zqr. Z is equal to 1. Q is 2, 180 times pi, and r is 3.5, 180 times pi. So this is the second equation for y. Okay? Again, simply took the numbers in the question and plugged them into the kinematic equation. Then we have the last one, z omega w dot is 0 equal to az, which is minus 3. Actually, I don't need to do this because I have two equations here, right? With how many unknowns in these two equations? Which are? U, V, and W, okay? So, one way to solve it could be to find the equation for Z, substitute the numbers, so that I have three equations with three unknowns, U, V, and W, okay? But there is another equation that I can use which makes my life slightly easier. What is that equation? Sorry? Using the angle of attack, which is given in the question as 5 degrees. So we know that tangent of alpha is defined as W over U. Okay, so U is equal to W is equal to U tangent of alpha. Okay, so now I have three equations, 1, 2, and 3. There are three unknowns, U, W, and V. Okay, so I can substitute this equation for W into here so that I solve for U. Okay, this is a number, this is a number, and these are two numbers with U. So I find that U is equal to U is equal to 80 meters per second. Okay. So with this value of U, I can find W, which is 7 meters per second. And with the value of U, I can go into this equation. With the value of W, I can go into this equation and solve for V. So V is equal to 3.5 meters per second. Okay, so now I have the three components of the velocity. So now I can answer the question. I can find Vf, which is given by the square root of U squared plus V squared plus W squared. Okay? And this turns out to be 80.4 meters per second. And then I can find the side slip angle beta from V over Vf. And this is 2.5 degrees. Is it clear? Any questions? No?
Y direction.
How many of you got this right? Hands up, hands up. Come on, don't be shy. No, but okay.
Yeah, quite good. So by comparing velocity that way, your plane velocity, you'll get side slip.
this set of equations for the velocity. Okay, so we have our aircraft. We have the probe, which is placed here, and this is the center of mass of the aircraft. So the vector R is the vector of the absolute velocity with respect to the probe. RA is the vector to the center of mass of the aircraft, and then let's call this RP, which is the position vector of the probe. Okay, so we can write that R, the vector R, is given by the sum of RA plus RP. Okay, if we differentiate this one time, we will get the velocities. R dot is equal to R dot A plus R dot probe. Okay. Now, this is the equation that we have to break down into components. This is the equation that we have to find. So, R dot will be the vector of the absolute velocities as seen by the probe, of the probe as seen by the observer. So we call this UP, VP, WP. Okay. What will be the vector RA defined by? RA is by definition the velocity of the aircraft. So UVW. So our only problem is to find R dot P. Okay? Because R dot P is the absolute velocity vector of the probe with respect to the center of mass. But we don't have any information. Okay? All the information that we have is related to the aircraft, not the inertial frame of reference. So, what can we use to bring the absolute velocity of the probe into a relative velocity of the probe? What do you know? What is that, let's say, mathematical relationships that you know that links an absolute quantity with a relative quantity? Sorry? Coriolis theorem. What does Coriolis theorem state? It's good that it's right. You can look at your notes, it's okay. It's not an exam. So, Coriolis theorem states that the relationship that exists between the absolute velocity, the absolute quantity of a vector is equal to the derivative of that vector in the terms of the relative frame of reference plus what? The angular velocity multiplied by that vector rp. Okay? So, for our system, the vector r dot p as seen by the relative frame of reference will be given by x dot p, y dot p, z dot p. Okay? And then we have the angular velocity vector omega, which is given by p, q, r, and the position vector rp, which is given by xp, yp, zp. Okay? Everybody clear? So this equation becomes here. So this is our equation. Okay. So for the omega vector rp, we have pqr, xp, yp, zp. Okay? So, let's write the kinematic equation. Along x we will have r dot a x. Here first. R dot. So, up is equal to the component of ra dot along x. U plus the component of r dot p in xyz frame of reference. I deleted it. Here it is. Plus x dot p. And then we have plus the vector product omega vector rp only along x. So this is given by plus q zp minus r yp. Okay? Is it clear how we got this equation? Yes or no? Yes. Okay, this equation here is expressed in vector form. Okay, what I need to do is to break down this equation along x, y, and z directions. Okay, so along I, j, and k unit vectors. Okay, so these are the components of this vector here along x, y, and z. These are the components of this vector. So this is r dot along x, y, and z. Okay. Then we have this vector here, r dot p. The components are x dot p, y dot p, z dot p. Okay. And then I have this vector product. Okay, the vector product of this along the x direction, so along the I unit vector, is given by qz minus ry. Okay, clear? Yes? Yes or no? Yes. Good. Now we do the same along y. For y, the component of the absolute velocity is vp.
This one is this one.
The relative velocity is v. The probe velocity is y dot p. And then we have the vector product along the j unit vector. So this is r xp minus pz. Okay? And then we have the last z, where we have zp is equal to z plus z dot p plus py minus qx. Yes, sorry.
Current line is more than the cross product. See y component line is a cross ratio. Use this one minus this one. Should be rxp minus pzp. Is he wrong?
Okay. Now these equations are slightly different from what appears in the question. So we are missing the aerodynamic angles alpha and beta. So what are the equations for the aerodynamic angles? We know that tangent alpha is given by the ratio W over U, and the side slip angle is given by the ratio between velocity along y and total velocity of the aircraft. So, we also know that a relationship exists between the velocity v and the individual components u square plus v square plus w square. Okay? Or we can get rid of the square root and take vf square So, from this, I'm going to here, vf square is equal to u square plus v square plus w square. So, we can write that vf square is equal to u square. And then we have v square, but v is equal to vf times sine beta. So v square will be vf square times sine beta square. Okay. Okay, so this here is v squared. And then we know that W is equal to U times the tangent of the angle of attack. So this becomes plus U square tan square alpha. So this here is W square. Okay. So I can take the v square sine beta square to the left-hand side so that I have Vf square is equal to 1 minus sine square beta. And this is equal to u, which multiplies, u square, which multiplies 1 plus tangent alpha square. Okay. So u is equal to Vf square root of 1 minus sine square beta over 1 plus tan square alpha. Okay. Everybody following? So, what we need to do now is to simply substitute the values for u, v, v is this one, sine beta, and w, which is this value, so w is equal to u tan alpha. Okay, so W is equal to Vf tan alpha times the square root of 1 minus sine square beta over 1 plus tan square alpha. Okay, so what you need to do is to simply substitute u into here, v into here, and w into here. And what you get are the equations that you have to derive. Okay, the second part of the question asks us yes, sorry, it's sorry. It's these ones here. UP, GP, and WP. Sorry. So you need to rearrange to have the same equations, because the equations in the question are solved as u equals v equals w equals rather than v w. Okay, the second part of the question asks us to determine what is the significance of the terms x dot p, y dot p, z dot p. So what do x dot p, y dot p, and z dot p measure? Yes, it's a velocity, but what is this velocity due to? Think of what x, p, y, p, z, p are, what these components are, and what is their velocity. What does the vector x, p, y, p, z, p measure? Position of what? Position of the aircraft with respect to what? Position of the aircraft with respect to the probe. The vector rp is the measures the position of the probe with respect to the center of mass of the aircraft. So what will the vector r dot p measure? The velocity of what? Sorry? The velocity of the probe with respect to what? With respect to? It's the velocity of the probe with respect to the center of mass of the aircraft. Okay? So, this is the center of mass, and this here is the position of the probe, and this is rp. How is the position vector rp, or its velocity, not zero, sorry, different from zero? If I measure a velocity r dot p, it means that the vector rp is not constant, right? If the vector rp is constant, its derivative r dot p will be zero. So, how is it possible that this vector, which is between two parts, 2 points on the same aircraft, varies? How is it possible? Is it possible, first of all? Okay. Who thinks that the vector rp stays constant? Hands up. Hands up, don't be shy. Don't be shy. So who thinks, remember that you have to vote. Okay, you can't keep your hands down. So, if you think that the vector rp stays constant, put your hands up. Hands up, not like this. Okay. So, keep them up, keep them up. So, who thinks that the vector rp varies? Keep your hands up, those who voted. So I see who doesn't put their hands up. Okay, let me retry. Try it one more time. Everybody has to put up their hand either for the first or the second question. Okay, it doesn't matter if it's right or wrong. So let's go again. RP is constant, hands up. Okay. RP is not constant, hands up. Keep them up. Okay. Those of you that think it is not constant, keep your hands up. Okay, is this a magic trick? Okay, why is it not constant? Sorry? The vector r dot p takes into account the flexibility of the aircraft and of the probe itself. So even though it may be a very small change, you may need to account for this to have an accurate measure of the aircraft velocities UVW. Okay, if you have this probe sensor, which is located, for example, near an engine, where there is a lot of vibration, this will lead to values for x dot p, y dot p, and z dot p, which are not zero. And therefore, you need to account for these values to have an accurate account of the velocities of the aircraft. Now, for most first order analysis, assuming that the aircraft is a rigid body is a fair assumption. If the aircraft is a rigid body, it means that there is no relative displacement between the 2 points. So if there is no relative displacement, there is no velocity. So as a first approximation, you can assume that RP is constant. But for a more precise and detailed analysis, you need to take into account the flexibility of the aircraft. Okay? And then we have the last question. Where you are given the values of angle of attack 30, side slip 30, and velocity 50 knots. Okay. And then we have a pitch rate of 30 degrees per second. And the position of the probe. So XP is equal to 5, YP is equal to 0, ZP is equal to 1. Sorry, 0. Okay. And you need to find, what do you need to find? You need to find U, V, and W. Okay. So you simply use these equations with these substitutions. So the equations that you have in the question, you plug in the numbers, tangent of the angle of attack, sine of the side slip angle, and aircraft velocity of 50 knots. You have only a pitch angular velocity. The other P and R are equal to 0. So you simply substitute the numbers. Remember, when you're using this to transform into radians per second. Okay? And what you find is that U is equal to 37.5 meters per second, V is equal to 25 meters per second, and W is equal to 24.3 meters per second. Okay, any questions? No? Okay, before I let you go. Okay. Next week, we will go through what are known as aerodynamic moments and aerodynamic coefficients, and this is, analytically speaking, the most complex part of the course. Okay, so everything that we've done now is easy compared to what's happening next week. I'm not joking. So I have already uploaded the slides for the next section on Moodle. Please have a look at them. And even though you may not understand everything that's going on, at least you will be somewhat familiar when we go through them next week.